now let's get on to our next topic, which is displacement and motion. So we're getting on to the application of derivatives and second derivatives to motion. So we're looking at displacement, velocity, and acceleration. So first, let's highlight the difference between distance and displacement. So distance refers to how far something has moved, and displacement is how far away something is. All right. So a pretty simple example of this is running a race on an oval, right? You know, you have an athletics day at school, that kind of thing. You're running a sprint all the way around the oval, and you're ending up where you started. The distance that you traveled was, I mean, it depends how big your oval is. Say it's 200 meters, right? I don't know how the circumference of an oval, but say you ran 200 meters, you've sprinted 200 meters, it was a 200 sprint. The distance you've traveled is 200 meters, but because you're ending up exactly where you started, your displacement is 0. All right? So distance is how far you've moved. Displacement is how far away you were from the beginning spot. All right? So as you can see, we have a diagram here. All right. The distance you might travel, say you are, you're rock climbing or bushwalking or something, you can't just kind of like take a straight path. You need to go around trees, around rocks, around mountains, that kind of thing. You have to weave your way around. So the distance you've traveled might be quite far around all these obstacles, but the displacement from your beginning point might not be that far at all. All right? The displacement is more so of like as the crows fly, as the crow flies. And distance is like, how much you actually track on your watch or your pedometer or, whatever you have. All right. A few questions. Can distance be negative? No, because you cannot ever travel a negative amount, right? But displacement can be negative, and that's because you can be because displacement includes the direction that you've traveled. All right. So let's have a look at the next diagram to explain. You can't ever go with a negative speed, right? Because it doesn't matter. You're always going at the same speed, regardless of what direction you're going in. But with velocity includes the direction you're going in. So if you're going to a positive direction, your velocity will be positive 25 meters per second. If you're going in the opposite direction, your velocity will be negative 25 meters per second. So, these are the values that you need to understand. And this is the relationship between all of these. So we kind of have displacement, velocity, acceleration, right? So if you're starting with a displacement function, to get to the velocity, you need to derive with respect to time, t, right? ds dt. So you kind of say that displacement is s. Sometimes you'll get displacement being x. It really depends on the textbook and the exam. Calling it s is more so of a physics notation, I guess. So if you're in physics, that might seem familiar. If not, that is just how we've chosen to represent it here. So you can kind of think about the relationship between them like this, just to kind of make sense of this in a more real world sense. If you think about your displacement when you are driving a car between point A and point B, your displacement might be 10 meters, all right? Your velocity when you traveled, all right, is in meters per second. So that's why we have the the measure of displacement over the measure in time. Measure of displacement over measure in time. All right, displacement over time. Meters per second. Your acceleration is in meters per second squared. So think about this even more. The acceleration is the derivative of the velocity, right? dv dt. So it's almost like the second derivative, or it is the second derivative of displacement. So it's almost like you're dividing by time twice. All right? So this is just kind of like how to make sense of it in the real world. And this is how I would remember it when I was starting out with the year 12 content. All right? Displacement is in meters, velocity is in meters per second, acceleration is in meters per second squared. All right, so remember, displacement is how far away you are, velocity is how fast you're going, and acceleration is how your velocity is changing, the rate of change of your velocity. All right, so remember, you can be driving along at a constant velocity, driving along a straight road at 100 k's per hour, you're on the highway, and you're not accelerating at all. Your acceleration is 0 because you're not changing speed. Say there's a 60 zone coming up, you're coming into a town, so you need to slow down. Your velocity is slowing down to 60, and your acceleration is also, you now also have an acceleration of like a negative value because you're slowing down, so your velocity is changing, right? Okay, as you can tell, to move between these, you can differentiate and differentiate to get velocity, and then differentiate that again to get the acceleration, and then you can also integrate upwards. So you guys likely haven't looked at integration yet, or if you have, your school might be a little bit ahead. So we're not going to focus too much on that today, but just make a note of it, and when you're coming back to these notes later on, you'll see the relevance. So now getting on to instantaneous velocity. All right, so the instantaneous velocity is not your average velocity over a certain period of time. All right, it's the velocity that you are traveling at in that exact instant. Okay, your average velocity, on the other hand, is the average velocity you're doing over a period of time. All right, so think about it again, going back to that sprint example. If you are sprinting around an oval, all right, typically what you do is you start off faster. I mean, I'm not a sprinter, so maybe this isn't typically what you do. I'm just kind of guessing here. You start off faster to get like a head start. All right, you maybe slow down a little bit in the middle, and then right at the end, you go as hard as you can. You go as fast as you can, all right, because you're like expending the last of your energy. So your actual velocity is changing over that time, or rather, your instantaneous velocity is changing over that time. Okay? So you're going faster to begin with, slowing down a little bit in the middle, and then going as fast as you possibly can right at the finish line. So your average velocity will give you one value across that entire sprint, and it will just average all those parts you're going super fast and all those parts you're going a bit slowly. So the instantaneous velocity is what you're going at an exact instant. Average velocity is like how fast you're going over a period of time. All right. So the average velocity is the rise over run, or just like the change in displacement over the change in time, whereas the instantaneous velocity is calculated using the derivative.